So this video is going to go over what we did in class last time, but basically how to power a 100-watt light bulb for 2 hours per day all year long, and how we would design a solar and battery system to do this. So the first thing we want to look at is a simple drawing of our system. We have the charge controller, where the PV is hooked to, the battery is hooked to, and the inverter is hooked to. Then the light bulb is plugged into the inverter. So what we're going to say is that our inverter is 50% efficient. So that's going to be one of our assumptions. And the first thing we're going to know is that we have a 100 watt light bulb. Okay? So we know the green numbers are going to be power here. The red numbers are numbers that we get later, and we'll come back to that. So first off, the 100 watt light bulb, if we do our equation and of efficiency, we know that 200 watts has to go into the inverter to produce 100 watts at the light bulb. So the first thing we know is that our charge controller is 200 watts. Now, in our systems, everything is 12 volts, except for after the inverter. So the charge controller, the battery, the PV panel, everything here before the inverter is 12 volts. So that's what we're going to assume. So the first thing we're going to figure out is how many charge controllers do we have to buy. So if we have 200 watts out of the charge controller, that's 16.67 amps. And our charge controllers are 10 amps, and I didn't write it here, but you'd have to buy 2 charge controllers. So now, let's look at energy. So now that we know power with the charge controller, for the PV and the battery, we really need to know energy because we need to know how many hours they're producing and how much the light bulb's using. So the first thing you want to figure out is how much energy the light bulb uses per day. So how we do that is 100 watts, and then convert it to kilowatts using this conversion, and then multiply by how many hours a day we're using it, and that is 0.2 kilowatt hours per day, and that's the light bulb use. So that's why we wrote that up here in red. Okay, so now let's go back down. Now we know that the inverter has an efficiency of 50%, and we know the output of the inverter is what's going to the light bulb, which is the 0.2 kilowatt hours a day we just calculated, and then 50% is the efficiency. So the input equals 0.4 kilowatt hours a day rearranging and using this equation. Okay, so again, we just figured out the 0.4 kilowatt hours per day, so we put that up here. Okay, so now the next step is to figure out, we need to generate that 0.4 kilowatt hours a day. So now we need to figure out how many solar panels we need. So we go to PV watts. If you just type in Google PV watts and you look at PV watts version 1, this is something you'll get. And we put in, for Delaware, we just did 1 tilt and azimuth, and that's down here. Yeah, we did 39.7 degree tilt and 180 degree azimuth. So that actually 180 means south, so that's what we did. And it's tilted about 40 degrees. So what you do is you design for what's called the worst month. So we're going to look at which month the solar radiation is the lowest. And in this case it's December, and it's 2.88 sun hours. So now we need to remember what sun hours means. And if we go down to the next, sun hours also mean that we have our 2.88 from above, but it also means that basically our solar panels are producing at full power for about 2.88 hours per day. So it's just an equivalent measure. It doesn't mean they're actually only producing for 2.88 hours and they're producing at max power. If it's a little cloudy for 6 hours and they're producing at half, and they about half, then they might be producing equivalent of 2.88 full hours that day. Okay, so we have to remember that our solar panels are 20 watts. Now we need to figure out how much energy would one solar panel produce. So if we do this calculation, one solar panel would produce 0.06 kilowatt hours per day. Okay, so now if we need 0.4 kilowatt hours a day and one solar panel gives 0.06, we would need 6.67 panels from this equation. but we'd want to produce more than that instead of less than that. We can't get 6 and a third panels, so we round up to 7 panels. Okay, so now we know how much solar we need. We know how many charge controllers we need. Now let's move on to batteries. So the big thing with batteries is you need to choose how long they should be autonomous, which means how long they should operate without sunlight. So this is going to depend on your climate, but we assume 3 days. And then we need to figure out how much energy needs to be stored to power our light bulb for 3 days without any sunlight. Okay, so in this case, we need to store 1.2 kilowatt hours. What's weird about batteries, though, is that battery capacity is measured in amp hours. So we have to somehow figure out how many kilowatt hours are in one of our batteries. So we assume one of our batteries is 15 amp hours. We multiply that by 12 volts because amps times volts equals watts. So we get amps times volts equals watts, and then we still have the hour. So we get 15 amp hours is 180 watt hours. Then we convert to kilowatt hours. Okay, so this battery stores 0.18 kilowatt hours. And since we want to store 1.2 kilowatt hours, again, it's weird that it turned out like this. It's not always going to be the case by a long shot. But we need to have 7 batteries. Okay? So the next step for your design would be looking at the parts list and calculating how much all this would cost. And the big thing you want to do is, first off, use a couple different results from your PV watts to see if that changes your cost. And you need to figure out, if you're the light bulb group, what type of light bulbs to use. If you're the pump group, you have to figure out, do you want to use the type of configuration where you have batteries or where you have water tank storage? Is that cheaper? And if you're the fridge group, you really have to figure out what the best orientation is. Hopefully that helps.